Okay, this presentation is about conditional probability. We're going to be talking about having how some events can affect other events. I'm going to start off using some notation, and the way this is written, the probability of A given B, so this is, say this mark is given, is the probability that an event A occurs provided that the condition B is holding. So we already know that by some reason that B has happened, and so this will see what's then the probability that A will happen. And we'll start out with these Venn diagrams. Again, as always, X denotes the whole sample space, and we have in this space two events, the event A right there and the event B right there. Okay, and A has little a outcomes in it, and B has little b outcomes, and there is X outcomes in the overlap. Okay. So if we're calculating the probability of A given B, we know that B has already happened, so this will be the number of things from A that are in B divided by B. Okay. Now, so it's as if we've shrunk the whole sample space, down to here. Okay, by this condition that we know B has occurred. So X divided by B is the probability of A given B. Now, we can do some algebra on this. We can divide the numerator and denominator both by capital N, the total number of outcomes in X. And so this will make the numerator the same as the probability of A intersection B, right? The probability of that, and this will make the denominator the probability of B. Okay, so brings us down to this formula right there. Okay, a beautiful formula. The way I remember it, the trouble is people forget, okay, which do you put on the bottom? Well, this thing that comes second will go down to the bottom, and this here, it goes up, and it's like they took this line here and bent it into that intersection symbol. Okay, however you can remember the formula, great. Now let's take an example of how to apply this. So at the elementary school where you are doing your initial teaching experience, 45% of the students have head lice. On a given day, 55% have runny noses, and 35% have both. They've hit the trifecta. What is the probability that that cute little kid that's running towards you to give you a great big hug has head lice if you can see from 15 feet away that he has a runny nose? Okay, let's do the math on this. Okay, the probability of having head lice in this group is 0.45. The probability of having a runny nose in this group is 0.55. And the probability of having both, okay, is 0.35. Now, here's the thing. You can see that he has a runny nose. Okay, you can see okay, you're thinking, what is the probability that this kid has lice too? Well, you run it through the formula, right? The probability of the runny nose divided by or dividing the probability of lice and runny nose. Okay, so we go through probability of lice and runny, yeah, right there. The probability of runny, and right there. And so here we have that we do the math on it, and it's 0.636, and you can't see, but I'm scratching my head right now. This problem always has this effect on me. Okay. Now, for a more pleasant problem, let's ponder this. Okay. Suppose that you are blindfolded. Okay. And then there's some candy. Some of the candy is red. 70% of the candy is red, and 30% of it is brown. Of the red candy, 20% is cherry and 80% is cinnamon. Of the brown, 10% is cinnamon and 90% is chocolate. Suppose you're blindfolded. What is the probability a piece of candy is red? Okay, that should be is red. If you can taste, it is cinnamon. Okay, we'll come back at the end and work on this. I'll give you the meantime to kind of ponder how to do it. Okay, independent events. We say that the events A and B are independent if the probability of A intersection B is equal to the probability of A times the probability of B. Okay. Now, this is not a formula that always works. This is a test. Okay. This is a test. Okay. If your events pass this test, okay, then they are independent events. Okay. But this is not always true, and I'm making a big deal about it because it's going to suck some of you in. All right, just mark this down. It's going to suck some of you in if you are not careful. Okay, now I'm going to start out with the supposition that two events are independent. So suppose they are independent, which means suppose, okay, just suppose that this is true. Okay, what effect does this now have on our conditional probability? Okay, our conditional probability, say the probability of A given B, is equal to the probability of A intersection B over the probability of B. Now, ordinarily, this is something we would have to figure out by counting it up. Okay, that's just the only way to it. This numerator, typically you're going to have to just sit down, get your hands dirty, and count it up. But here we have made this supposition that they are independent, and therefore this holds. So in this special case, we can make this substitution. Okay, in this substitution, I substitute in PA times PB for the numerator. And so in this special case, hey, I get to cancel out the probability of B from numerator and denominator, leaving just the probability of A. So what is this saying? It says when A and B are independent, then the fact that B happens has absolutely no effect on the probability of A. That is what being independent is about. Okay. Okay, so some examples. Okay, flipping a coin. If you flip a coin and it turns up heads, the coin does not remember. It cannot, flipping it does not affect what will happen on the next flip. Just because you hit a head this time does not mean one way or the other that you'll flip a head next time. Okay. Now, sampling with replacement. If you have a jar of blue beads and red beads, and you pull out a blue bead and then replace it, you've not changed the probability of pulling out a blue bead or a red bead next time. So those are independent events. Okay. So the way we do this in calculation is, what's the probability of flipping ahead and then flipping ahead again? Well, probability of getting it the first time was 0.5, and there is no effect because the probability of getting it the next time is 0.5. And so the probability of flipping ahead 2 times in a row is 0.25. Okay, what's the probability of getting a head and then getting a tail? Well, again, getting a head the first time, 0.5. Getting a tail on the second time, 0.5. Getting a head and then getting a tail is 0.25. Okay. Alright, sampling with replacement. So a jar has 700 red beads and 300 blue beads. Okay. You choose a red and then choose a blue. That's a 0.7, a probability of getting a red on the first time, and a 0.3, a probability of getting a blue the second time. Probability of getting a red and a blue is 0.21. Probability of getting a blue and a blue, okay, a 0.3 the first time and a 0.3 the second time, be a 0.09 to get it both times. Okay, now I promised that we would talk about the cherry candy example. Okay, and so we have this candy. It comes in cherry, and it comes in cinnamon, it comes in chocolate. 70% of it is red, 30% of it is brown. Of the red, 20% of the red is cherry, 20% is cinnamon. There's no watermelon, thank God. Of the brown, 30% is cinnamon, and 30% of it is brown, 10% of it is cinnamon, and 90% of it is chocolate. Now, how do we solve this? Well, here I decided it was better not to use any fancy formulas. I just said, okay, suppose that we've got n pieces of candy together, then 0.7 times n of them are red and 0.3 times n of them are brown. Okay, so let's then break it. We've got it broken down by color. Let's break it down by flavors. So 0.2 times the red, so 0.2 times 0.7 times n is red and cherry, and then 0.8 times 0.7 times n is red and cinnamon, and 0.1 times 0.3 times n is brown and cinnamon, and 0.9 times 0.7 times n is brown and chocolate. Okay, so how much, so you know that it's red. How much of the candy is red? Well, you add up all of the red candy, this 0.1 times 0.3 times excuse me, we know that it's cinnamon, we know that it's cinnamon, so you do 0.1 times 0.3 times n to get you the brown cinnamon, and you do 0.8 times 0.7 times n to get you the red cinnamon. So the bottom is cinnamon. How much of the cinnamon is red? Well, you put the 0.8 times the 0.7 times n to get you the red cinnamon on top. The n factors as a common factor out of the bottom, and we can cancel it from numerator and the denominator. This gives us 0.56 over 0.03 plus 0.56 on the bottom. You do the arithmetic on it, and it comes up, if you can taste it, it's cinnamon. There's almost a 95% chance of it being red. Okay. So you can, in this case, you can almost taste the color.